So we're going to solve exercise 3 from my compact Lie algebra course. Oh no, not compact Lie algebra, it's actually compact Lie groups course. But anyway, what we need to show is, let me check the problem statement. The first part of the exercise is about we need to compute the killing forms for each Lie algebra. I mean sl2r and su over r, and we need to show that this guy is compact and this guy is not compact. The definition of compact Lie groups are given as we need to compute the killing form, and the resulting killing form needs to be negative definite for it to be compact Lie algebra. And yeah, the first part is we need to compute killing form of su2 over r, which is kind of important because the second part actually talks about if we complexify the Lie algebras, then we actually get isomorphic structures. And yeah, I don't have particularly good knowledge of Lie algebras by themselves, so I will be speculating a lot. And if my shallow knowledge is correct, then I think there are some certain relationship between the classical Lie algebras over the complex numbers that makes relatively low dimensional ones isomorphic by themselves. And yeah, we need to compute those, conclude. The first part, su2r is compact and sl2r is not compact. And the exercise asks as a corollary to the first part to conclude that sur is not isomorphic to sl2r. I have an immediate, so to say, concerns about the formulation itself. So I mean, this is the fact that the first part implies the second is pretty much obvious in a sense that if one is compact and the second one is not compact, then it means their algebraic structure is quite different. Yeah, and it should mean that there are some things that cannot make them equal. Yeah, so my like it is probably a little bit being too paranoid. But anyways, what I think was trying to do initially was I just didn't read the first part, and I was just reading the second part, and I thought, like, why do I need to check compactness and non-compactness? Because well, if you just show that for some killing form, not for some, but I mean, you can have a like sort of base change of killing forms over it, over some different choice of basis of Lie algebra, right? And the resulting killing form matrix representation will be pretty much different depending on the basis. And what I was thinking of is, shouldn't it be like failure to be similar lead to the second part? I mean, it's not strictly speaking if and only if relationship, if I get it correctly, because like if they are isomorphic, their killing forms must be in a how to say it, the congruence relationship. Yeah, I think this one is called congruence relationship, and this should be a sufficient condition to conclude the fact that they are not isomorphic. The reason of my argument is obviously the fact that killing forms are invariant under automorphisms. As Lie algebra, obviously. Yeah, that was my first concern, but yeah, I don't know what I wanted to say, but what I thought is pretty obvious is use this argument to show that they are not isomorphic, which is subtly implied by this one. Not subtly, I would say pretty much explicitly. But anyways, my impression is that I want to argue by this when I were to conclude the second part. So let's start. Let's first pick a basis for both Lie algebras so that we can work in a concrete computational manner. Because we'll be doing a lot of matrix multiplications, and to be honest, I don't want to do matrix multiplication, so I'll outsource the matrix multiplication part to Python. Like I need to, the killing form definition is given by the trace of adjoint x composed with adjoint y. Here comes another my shallow knowledge. I don't know how to properly compute adjoints. I think there should be a way to do it using Jacobian identity, but I'm a pretty dumb person, so I will just represent adjoint some with respect to some basis as certain matrices, and then compose the matrices. And since the trace of my base will be spanning the whole sl2 with respecting the Lie algebra structure, I mean, why not? So I think sl2 case is more straightforward one at the moment, because we have some things to talk about here, I guess. And because of that, I will just call E1 as the trace part, E2 as the raising part. I'm borrowing some terminology from the representation theory of Lie algebras, which I don't think it's covered for as of now. The omitted entries are zeros, because it's 2x2 matrices. I think I can do it still without being ambiguous. You will hear some church bells here because I'm currently studying in Germany, and they are letting me know what time is it every time. Actually, every 15 minutes. The classical definition of adjoints are something like if you have EI applied to EJ, it's EI, EJ, the brackets. Yeah, this is how it's defined, but in a concrete computations, it's gonna be EI, EJ minus EJ, EI. Physicists call it commutator, but whatever. I used to study physics, but not anymore. There are some remarks about this if we talk deeply about some abstract representation theory, Lie algebras, for example. Like the notions of universal enveloping algebra and so on. But in our concrete case of matrices, I don't care about them. So I will borrow some. I will cheat a bit and borrow some formulas from the classical results. I mean, you can actually do the actual computations using this formula, which I find it quite unnecessary in a sense that by the time you know about the algebra, you'll know how to multiply matrices, right? And I will skip diagonal entries as of now because diagonal entries are obviously zero because we have a commutator, and yeah, if I equals to j, you can just flip it out and you will get 0. And with respect to raising should be E2, and by the fact that it is a commutator, it should be minus adjoint E2, E1. And with respect to E1, E3, it's lowering, and we get something like this. I don't know where to write the relationship. This is straightforward computation. You can just multiply 2 by 2 matrices, subtract them, and to get the correct result. I hope I didn't make any typos here. And let's represent them as matrices with respect to our choice of E1, E2, and E3. Because we have chosen basis of size 3, which is like it might sound counterintuitive at first if you are new to Lie algebra, but in this case we have three sort of free variables running across the real numbers. So yeah, we have this, and what we get is 2 here, but we input 2 and goes to 2, so we have 0, 2, and what else? E3 minus 2, minus 2. So it's gonna be a diagonal matrix of 2 and minus 2 and 0. And for ADE2 we have to find, so E2 applied to E1 is E2, so we need to act on by E1, and almost all entries will be 0. What else? I'm missing something. Yeah, E3 goes to E1, which means the matrix should look like this. I mean, I'm under this choice of basis vectors, and for A3 we need to do, it's going to be a little bit strange, like it's not a full transpose if I get it correctly, and this off diagonality is driving me crazy sometimes. E3, E1 is 2, E3, so it's here 0, 0, 0, 0, 0, 0, and which one? E3 applied to, oh, I forgot minus here. E3 applied to E2 is E1, which means minus 1 should be here. Like, it's not strictly saying transpose, right? And I'm sure there, I'm actually not sure, but might be an alternative choice will make them and somehow have some symmetric relationship, but I didn't care that much. And what else? Okay, so what we need to do is I want to represent killing form as a matrix over basis vectors. So yeah, I will just represent it as a sort of matrix entries over EI, EJ. And I did just run the Python script that computes the tray, does the matrix multiplication and computes the trace to get 8 0 0 0 0 4 0 4 0. I actually computed only this one and this one because actually you need to know only this upper triangular part because you don't really care about the lower part, not because you do not really care, but because the definition of killing form gives you quite immediately that it should be a symmetric one, like because the trace of ADX ADY, this is matrix multiplication. So what it gives is it's a classical result of linear algebra that trace, like trace of AB equals to BA, and well, to conclude that it is compact or not, we need to find its eigenvalues, which we'll do by just classical eigenvalue polynomial. I insert lambda here, here, here. So what we get is do I care about sign? Anyways, it doesn't really matter because it's order 2 polynomial. Strictly speaking, I need to do this to be consistent with the notation. But we get at the end 8 and plus minus 4. By the definition, we know that it's not compact then, because it's not negative definite. Now let's try. I don't like this particular way of writing, but So we are choosing the basis for su2 over r, which is important. What do I have? Suppose I want to choose first over reals, then it's gonna be 1 and minus 1. And then over the imaginary, because, oh, sorry, I forgot to write this thing. And it's gonna be imaginary, and we do flip, then minus. So it's gonna be off diagonal ones. Okay. All right then. What we need to do is, okay. We need to compute the matrix representation of a joint. I will come back in just a moment. I will just run the code to get the answers. So yeah, I ran the code and I got the E1, E3, E2 is equal to E3, which is minus AD, E2, E1, AD, E1, E3 is equal to E minus 2, E2, and the rest is just straightforward filling in. And I think the contrast here from here is pretty obvious. Of course, this adjoint relations will be dependent on the choice of basis, but yeah, the so to say, E1, E2 goes to E3, and then E1, E3 goes to E2. Yeah, that is already a little bit different. Like in sl2 case, we got E1, E2 to E2, and it already starts to feel like it's a little bit different. And for the matrices, we get 1, 0, 0, 0, minus 2, 0, 2, 0, 0, 0, 2, 0, 0, 0, minus 2, 0, 0. And let's finish the filling up, although it's not so relevant in a sense that, okay, I ran the code and we got diagonal matrix. So killing form that we got is and I think I messed up something. Oh no, I didn't mess up, because the characteristic polynomial will be cube, which is just, oh no, not this one. We get this one cubed to be equal to 0 to find the eigenvalues, which means that lambda is -8 with multiplicity of 3. So what we got is, so we have only negative eigenvalues, which means su2r is compact. Okay. I don't know if the lecture covered that compact cannot be to the non-compact. So I think I'll argue with myself that I don't know if how is it exactly called? The Sylvester's theorem, I guess. But the two matrices K, well, this K and that K, I will write SL and SU. SL and SU cannot be similar because the eigenvalue signs are different. I think it's covered by Sylvester's theorem. It is something like the two matrices cannot be similar if they have a different eigenvalue signs. By this I mean, so for KSL, we have a plus minus plus plus minus, and for KSU we have minus minus minus. So we cannot make them similar by this guy's theorem. Yeah, and so KSL cannot be congruent. KSL cannot be congruent to KSU. So we found the necessary condition that was failed to be whole, because if the Lie algebras were to be isomorphic, then there must be a way to transform one killing form to the other. But because they cannot be congruent by Sylvester's theorem, yeah, the killing forms are not congruent. Thus, their Lie algebra cannot be isomorphic. And I think that completes the first part. Yeah, I think that completes the first part. So, since we did the first part, now we'll be doing the second and third part, which is about the following statements. What we need to do is to show that the complexification, like the algebras that we were dealing with, su2 over r and sl2 over r, become isomorphic on complexification. I think I did some remark about this one, particularly I think I told you that this special Lie algebras, or not even specials, but relatively lower dimensional classical Lie algebras, which include special unitary and symplectic also, I think, are isomorphic under if the underlying field is complex numbers. I might be a little bit too naive to state this one, but anyways, at least for SU2 and SL2 we will now demonstrate it. So the problem statement is that let this be the basis of SU2 I probably should have used this combination of numbers, combination of symbols to denote the basis of su2 and sl2 when I was solving the previous exercise, because I mean this is more sensible in some sense. Like ijk, the choice of ijk is pretty much clear why we are doing this. I guess it is related to the certain sort of cyclic relationship of ijk in quaternionic algebra. It's just a speculation. Like if I, as a former physicist, if I see ijk, I just immediately think about quaternionic algebra. And I need to express them in terms of sl2 basis, which is something like this. I guess sometimes it is the standard way of writing this one is x and this is y and this is h. H is pretty much universal, I guess, because I think it arises due to this one, this Cartan subalgebra. And yeah, so what we need to do is to write ijk in terms of EFH, but under when we extend the scalars to complex numbers. And I think this is pretty clear in a sense that we can just think naively. Wait, this is not trace 1. This is not trace 0. Yeah. Is it? Oh no, I wrote the inverse direction, so let's see. Oh, I mean I could just write minus I, but anyway, let's have some consistency over here. And if so, j is just minus e plus f, and k is minus I e plus f. This is a little bit naive way of writing, I guess, but this is also correct one at the end. My impression is that it is the correct one. Not because I think that like we can just put it i's here, but so the definition of complexification is something like we just imagine that every entry is having a scalar extension to complex numbers. So by this, in a strict sense, I should be writing something like this. If you are meaning about the extensions of scalars in the following sense, and this is in a less abusive notation, mean and this one is precisely this thing. Yeah, and I guess this is all that was being asked. Not because well, I mean, the Lie algebra structure is clearly, obviously, like satisfied, because the way we define the how Lie bracket behaves under complexification, like it is some sort of the real part, and some cross terms, and then the imaginary part, and right. Like there are some compatibility condition that we impose on the Lie brackets under complexification, which makes the Lie algebra structure work, and it will agree with the initial complex initial, like if we think about embedding sl2 r to gl2 over complex. Yeah. So the third part is the following. The problem statement is a bit strange in a sense that it reads as following. Like in class, we introduced the standard representation of C2 and their symmetric nth power, which we denote by SNV1. And in the class, we show that it is irreducible. Representation of SU, and it continues as its differential gives an irreducible representation of SU2R. Hence also of sl2C, which is isomorphic to sl2C, and I think this is what I don't need to prove, if I understood correctly. Like the first part had explicit in the class we introduced, and the second part I might need to prove it, but I don't want to, because I mean because we started with the SU2, and to do it I need to take the differential, which I find it to be a little bit messy. Like I prefer thinking of Lie algebras separately from Lie groups. Like, I mean, it's not I would say that once I tried to be a geometer, but and I find this Cartan decomposition to be a beautiful piece of work and beautiful piece of beautiful point of view of how Lie groups behave. But the reason I'm studying representation theory in general is because I got very motivated by the sl2 over C, which I find beautiful because this how EF and the adjoint representation of sl2 dictates how we can decompose the finite dimensional irreducible representations of sl2. By this I mean the weight decomposition. It approximately goes something like, because we have the h of e is 2e, we can the structure, or this particular structure would mean that the eigenspaces like this finite dimensional irreducible representation have sort of eigenspace decomposition, which makes each eigenvalue integers, and the particular actions raises the eigenvalues by integer. And because the irreducible representation we assume to be a finite dimensional one, it should terminate at some point, and because it terminates, it must have some integer values. I mean, the explicit construction, the final conclusion that I made that it should have integer values comes from the interaction between E and F, and how H behaves under it. But anyway, it's not that important for our concrete case. And regarding the symmetric powers, and symmetric powers are actually the first thing that introduced me into combinatorial aspects of the algebra. Not the symmetric powers itself, but how Sm(v1) tensor Sn(v1) behaves. It's I think it's called Clebsch-Gordan problem or theorem. I don't exactly remember the word, but anyways, so how it behaves is really interesting. I came up with my version of the proof, which is just saying that symmetric powers has some sort of like intervals of on the weight line, so to say, and then this is just about the observing sort of intersections of those weights appearing in symmetric powers. And yeah, I found it beautiful, and here I am. And so yeah, well, let's get back to the problem itself. It's about basis vectors. So what we need, the problem statement is the following: compute EFH actions on the standard basis. E1 and so on till E2n of Vn. Oh gosh, again church bell. It's gonna, since it's 9 p.m, it will ring 9 times. You might want to count if you're a little bit bored. So before doing this, I think I need to talk about how the algebra actions behave under tensor powers. But before doing that, I think I first want to compute the actions, the standard actions, which is E is 1 and E1 is 1, so it's 0. E2 is by this I mean 0 0, obviously. Then it is 1 0, I guess. And then we need to compute EF, E1. Hope I'm not messing up anything. Oh, the moment I told you, I almost messed it up. 1 2, okay, that looks fine. By symmetry argument, it's gonna be 0. Then I need to compute HE, which is, I expect to be just E1. HE2 is probably minus E2. I hope everything is correct. Yeah, and I had to talk about how tensor powers behave. Basically, it behaves like derivation, in a sense that suppose we have some vector Is x? No, I think I don't want to pick x and y for it. Let v be do I want this? Let me take pure tensors because derivations are linear, so we don't have to worry about if it's pure or not. We just decompose into pure tensors and then act on it in each pure tensor. And yeah, suppose we have x in this Lie algebra. Specifically, I will mostly think in terms of sl2 because it's a more familiar thing for me. And if so, x on the tensor as a derivation By the way, I want to quickly tell you about the disclaimer. A lot of things that I'm talking about is I try to be explicit as possible, but a lot of things are speculations. That in other words, I'm guessing. And yeah, this is the derivation. And in more advanced topics, I think I don't know the exact motivation behind it, but I will still tell you something. Like I think this is called so to say co-multiplication in a coalgebra structure, which means that something like there is a thing called Hopf algebra, and we can think about this one just a regular Hopf algebra operation, because this one in certain sense from this on it is a pure speculation. This Hopf algebra structure simplifies the algebraic dirtiness of the way that how Lie algebra acts with respect to not symmetric powers but tensor powers, tensor products. And yeah, to be honest, I forgot. I think I knew what is the motivation behind introducing Hopf algebras, but not anymore. So what we need is how it acts, and we need to use these relations. This is E2, right? And wait, I hope I didn't mess it up. I think I wrote down something. Yeah. This is E1 because E2 applied to E1 is yeah. If so, everything is fine. And I think you can immediately see sort of my hint about weight decomposition. So, for example, E applied to E2 goes to E1, which has eigenvalue of 1, and F applied to E1 gives you E2. And E2 has eigenvalue of -1, so their difference is 2. And I think I told you about weight decomposition and the reason why E and F are called respectively raising and lowering, it means that it's raising and lowering eigenvalues. Or in standard terms, we call it weights. And there is a whole lot of theory of highest weight modules, and a little bit more sophisticated thing is, I think, the category O, which we talk about the sort of locally finite weight modules, and how something called the standard module behave, and that direction is full of this categorical and abstract nonsense, which I'm trying to understand, but it's a little bit hard for me as of now. And yeah, now we need to explicitly compute all these things. It's like I don't want to invoke Hopf algebra structure to do this, because I think this can be done purely in terms of this derivation relations. And yeah, so suppose we have this thing. What do I want to do is, I think, something. No, I think En is a bad way of writing it. Yeah. What if I just write like this, and we just compute the actions? Should I? From where do we start? How E acts on it. So we have m times E1, first the derivations, which goes to 0. Then we care only about E2. E2 n minus m times, and we have sort of a little bit problematic that it won't be in sort of a lexicographic order. Like what happens is, okay, I need to be a little bit careful here. From 1 to, it happens n minus 1 times, so n minus n of E, apply once, twice, thrice. No, not like this. I need to somehow mold it into here. Well, M survives, that's for sure. Then E2 is before it, I minus 1 times, then E1, because we applied it here. Then we need to conserve this total power. EMI n minus mi E2. Yeah, I think this is what we have. For F, I think no, F is also a little bit non-trivial. So yeah, we apply this thing m times to like m times non-trivial action. So we need to simulate this thing here. E1 I minus 1 E2 we have ones, and now m minus I, right? Yeah, m minus and n minus m. Let's quickly do some sanity checks. Does it sum to n? Yeah, I think so. And how h acts to it? H doesn't change the powers. It only counts if it was E. I guess it's then m times we get plus and minus n m. What do we have? Is this correct? I think so. Is it? I hope so. Anyways. If I'm incorrect, I'm incorrect. Whatever. Now we need to express them in terms of do we care about lexicographic order? Do we care? It's symmetric tensors, right? If so, we just have to count, right? Yeah, we just have to count. I think this was pretty much unnecessary. If so, I mean, I was thinking about the alternating tensors instead of symmetric tensors. Oh yeah. So we just have what are these subscripts? 1 second. What? Yeah, E1, E2. Yeah. Then it is we apply it and then oh wait, we have m times E1 m minus 1, right? Yeah, and E2 n minus 1 n minus m plus 1. Then we have here n minus m times like this. I just want to quickly check the edge cases. What happens if m is 0? M0 is we need to care only about m is n then this whole thing is just E1, and E1 should get killed entirely. It's highest weight vector, and so we have 0. Yeah, it's alright. And this case is, oh yeah, it is easier to see, and we have sort of highest weight and lowest weight cases. Yeah, it looks fine. I might have messed up some things, but it looks like we have the actions in a general form. So yeah, it looks fine. And it concludes the exercise, I guess.